Yeah, thanks for the kind words of introduction, and specifically to the organizers for having me here and the opportunity to present some of the recent research in this context. So I'll talk about global climate and energy scenarios towards 2050, so taking away a step back to outline the problem in its totality. So I'm going to touch upon essentially four big questions. What are challenges related to reaching the 2-degree target? What are the investment needs for getting the energy system there? And we'll briefly comment on the 1.5-degree target, which is an important aspect of the Paris Agreement. And then toward the end, we'll talk about interactions between climate policy and other sustainable development objectives. And here, the SDGs have already been mentioned. So the first topic, you will have, many of you will have seen this or similar figures. This is a compilation of where the INDCs will get us by 2030 in terms of global greenhouse gas emissions, and how does that compare to least cost scenarios or pathways towards 2 degrees or even 1.5 degrees. So what you see up here is there is a considerable uncertainty range, and this has been confirmed by other studies. So INDCs are expected to get us, if there is no increase in the level of ambition embedded in them, to something like 50 to 60 gigatons CO2 equivalent emissions, but actually quite a bit more would be needed to get us on a cost-effective transformation pathway towards 2 degrees, not to speak of 1.5 degrees. And so one of the challenges is to make sure that within the process of the Paris Agreement, this so-called ratcheting up process, so increasing the level of ambitions will close that gap to some degree. And I will comment on some of the challenges that we are facing if that happens or if that doesn't happen. So first let me take one step back and outline a generic mitigation strategy in the energy system. Consists essentially of 3 parts. One is the decarbonization of energy supply. We've heard Norway is very far along this line. Second is reducing energy demand in different sectors by implementing efficiency measures, but also through structural change. And then last but not least, switching to low carbon fuels. And here also Norway is, it seems, taking a pioneering role in moving the transport sector, or at least a good chunk of the transport sector, light duty vehicles, towards low carbon fuels, that is most notably electricity, but could also be hydrogen in the future. So how does the supply side of things look like? In principle, what we need to do is increase the share of low carbon primary energy from where it stands now. The 2010 numbers are around 15%. That hasn't increased very much over the last 5 years or so. But where we would need to get in case we really are on a cost-effective trajectory, this is the left-hand column in green here, the immediate case, by 2030, this share should roughly double to be on this cost-effective pathway. If we are on a more relaxed timeline, such as the one outlined by the INDCs, we may make a little bit of progress, but that may not get us to the cost-effective way of implementing things. As a consequence, if you still want to maintain the possibility to curb temperature change to 2 degrees, the level of effort that will need to be invested post-2030 is dramatically different. While in the case where we immediately move towards a 2-degree pathway, another doubling of this low-carbon energy share to 50 to 60% would be necessary. In case we maintain or we stay on track with the INDC level of ambition, a quadrupling or almost a quadrupling would be necessary between 2030 and 2050, indicating that we're just pushing off some of the large challenges in this context. So by the end of the century, obviously, most of the system would need to be reliant on low carbon energy sources. To make the challenge a little bit more tangible, here are upscaling rates, so annual capacity additions at the global scale under the 2-degree target, compared to what we've seen historically. So both in this immediate case where we significantly raise the ambitions embedded in the INDCs, and then only and then in red here, the levels of deployment, of annual deployment that would be consistent with doing this only after the INDCs. And then in blue, I put next to this historical levels of annual capacity additions. And if you did plot the same figure only 3-4 years ago, it would look much more pessimistic if you looked at the levels of wind and solar deployment. But there has a lot has happened. Solar, we have witnessed 75 gigawatts of PV capacity additions in the last year, half of which was China. The rest spread across the rest of the world. So that gap is closing. Where it is actually remaining to be a big challenge is carbon capture and storage, and that challenge was just highlighted previously, where we are not beyond the demonstration scale. But if that technology is supposed to play a significant role and manage the transition also of fossils toward a low carbon future, a lot will need to happen. The other side of the coin is, one side of the coin is upscaling, bringing in new technologies into the system. The other side of the coin is actually retiring, possibly prematurely retiring existing assets that are fossil fuel assets. So this figure shows an example for coal-fired power plants. And what you see here on the x-axis is this range of greenhouse gas emissions by 2030 that is consistent with the INDC range. So being either on the low end of the INDC range, so around 50 gigatons, or on the high end of the INDC estimated range, so closer towards 60 gigatons. And then we see the value of stranded coal power capacity in black in the near term, so up to 2030, and then post-2030, so 2030 to 2050 mostly, in the shaded color here. So what you see is, if we are aiming for the more ambitious target in the near term, so if we are successful in ratcheting up the INDCs, we may need to prematurely retire more in the short term. However, if we push that ratcheting up off, then it will hit us even harder in the long term. So one strategy that seems to work here is put a lot of effort in efficiency, which means that remedies essentially the need for building a lot, for adding a lot of the generation capacity in the decades to come. This is specifically true for developing countries and emerging economies. That could be a dominant strategy here. Let me also take a closer look at the regional breakdown of where we would find these stranded assets mostly. And as you can expect, they're there where currently a lot of the coal capacity is still being built, so mostly in China and India. And this will also be the capacity that would have to be retired post-2030 if we then embarked on a serious 2-degree mitigation trajectory. On the other hand, developed economies such as the US or Europe would most likely have to retire some assets in the near term, but there isn't much new capacity anyway being built, so it's less prone to the risk of premature retirements post-2030. So what are the levels of investments that go along with these 2-degree compatible energy transformations? This is a study, kind of a meta-analysis of investment needs. One takeaway is actually, this includes, for instance, the well-known IEA estimates, then there's the global energy assessment in there, and estimates from 5 different models. One takeaway here is we roughly know how large these investments are, but you should be skeptical if you are presented a single number, because even for the present, it's kind of hard to estimate. And in particular, if you're looking at energy demand type investments, there are large definitional questions, how are these defined? So ballpark, we are at the moment talking about $1 trillion per year, ballpark 2% of global GDP that go into the energy system. That would need to significantly upscale out to 2050, even under a current policy case, which would likely lead us to something like 3-degree temperature change. There remains to be a large uncertainty, A, on the magnitude, and B, on the composition exactly where this would go. And then transitioning to a 2-degree future, there's another upscaling of investments needed. However, more importantly, it's a complete reallocation of investments across different technologies and sectors that would be needed, including a very significant upscaling of energy efficiency related investments, plus enabling policies to overcome existing barriers. So here also, again, very important that there isn't a single number for this. There are multiple strategies, and depending how your mix of strategies at or the mix of measures at the national level looks like, these numbers could actually come out very differently. If we look at the clean energy investment gaps, so this is investments into renewable energies, nuclear, as well as energy efficiency. In blue here in the current policy case, and in white on top of that, what would be needed for getting us to 2 degrees, you realize that there is a very significant, there is a significant upscaling needed of investments in these clean energies. Plus, most of them are actually going to occur in developing countries. So 70% in developing countries, only roughly a quarter or 30% in the industrialized world. So how does 1.5 degrees compare to 2 degrees? I'll just show this in a single slide using this radar graph. If you normalize the effort that it would take to get to 2 degrees and then look at different cost and mitigation emission reduction metrics, what you end up with is there is a significant need to upscale the short-term investments. So short-term action is really crucial for maintaining the 1.5 degree C scenario target in view. And most of that action would actually need to be focused toward demand-side sectors. So curbing energy demand is here a really crucial strategy. I've talked you through this, so let me come to the last topic, that is looking at the interactions between climate policy and other sustainable development objectives. SDGs have been mentioned. I won't be comprehensive, don't worry, there won't be 16 slides on the interactions between SDG 13, climate action, and others at all. Just to look at the big picture, this is a compilation of potential co-benefits and adverse side effects of the energy transitions in the context of the 2 degree target. What you see is essentially in the columns a range of economic, social, and environmental dimensions. Green arrows show co-benefits, orange arrows show adverse side effects. In the upper part, that's supply-side measures, including, for instance, nuclear, carbon capture, and so on. Lower part are different demand-side measures, including efficiency in the different end-use sectors. The takeaway message here at large is you see a lot more green arrows in the lower part of the picture. So efficiency has typically the advantage of generating more co-benefits than adverse side effects, where on the supply side, the mix of both issues is more heterogeneous. Let me now look more specifically at the interaction of climate policy and 2 specific SDGs, most notably the hunger SDG, SDG 2, and the health SDG. Let me start with the latter, and this is actually a relatively well-researched and documented issue. There are significant co-benefits between climate policy and air pollution and related health impacts. The reason for that is that many air pollutants, including here for illustrative purposes black carbon and sulfur emissions, are co-emitted in combustion processes of fossil fuels that are phased out when implementing significant climate policies. What you see here is the development actually mostly driven here by, so this is a non-climate policy case where existing air pollution legislation is actually the main reason for dropping emissions. But then if you, on top of that, add INDCs and the 1.5 and 2 degree scenarios, you see actually out to 2050 quite significant reduction of air pollutant emissions as a co-benefit of climate change mitigation. That brings me Yeah, actually, this is the regional breakdown of that. Here, one interesting insight is the co-benefits obviously also vary with the level of ambition embedded in the INDCs. So some regions, including for the European Union, show actually quite significant co-benefits of the INDCs already for air pollution and related health impacts, whereas other regions with much lower ambition embedded in their INDCs, this is typically not the case, and only transitioning to 2 degrees or 1.5 degrees scenarios would get a lot of the co-benefits on the air pollution side going. That brings me to my last topic, food security. That's an issue where that has known to create trade-offs between climate mitigation policy. So one of the important takeaways here is we will need supplementary measures to avoid or to mitigate these significant trade-offs that could potentially materialize in this context. So first of all, on the left-hand side, you see the FAO estimate for the population at risk of hunger. In the year 2005, about 800 million people were classified as that. How this evolves out to 2050 is sketched here in the reference case, the red bar. A big caveat here is, next to climate policy, this is very much dependent on how socioeconomic development will continue over the next 30 years or so. So there's a large error bar. We used a kind of a medium, actually quite optimistic projection, which leads to a significant reduction in the reference case. But what is more important here as an insight is if you add climate policy, either at the level of ambition of the INDCs, compatible with 2 degrees or 1.5 degrees, if that climate policy is narrowly focused on mitigating emissions, you may actually put a lot more people at the risk of hunger. There are essentially 3 mechanisms that contribute to that. On the one hand, agriculture itself is pretty emissions intensive. Therefore, we would see a significant increase in food prices through that mechanism. Secondly, there is competition over land between bioenergy production and food production, which also contributes to an increase of prices. And third, that through climate policy, a lot of products may get more expensive, so might be an income loss for people that would need to be compensated. So it's important to think of complementary policies that reduce this adverse and clearly undesirable side effect, which mostly affects low-income households in developing countries. So the hotspot for this to happen would be sub-Saharan Africa and also parts of South Asia. It would clearly be an option that may not be at zero cost, but compared to the investments needed in the energy transformation, the numbers are quite a bit smaller. That brings me to my concluding slides. So on the one hand, we need to create an enabling environment for rapid upscaling of low carbon supply options. This seems to happen in some cases, so that's actually good news. Managing the stranded assets to get buy-in from industries that are heavily into the fossil fuel industry is important. Increasing the investment needs is something we will have to face, given that energy is only a relatively small fraction of total investments. That might be doable, so with the right incentives in place. Focus on 1.5 degrees needs short-term action very rapidly, in particular on the demand side. And then to manage or to get buy-in also for climate change policy, it's important to look at integrated solutions that do manage the trade-offs between climate mitigation and other policy objectives. Thank you very much.